it's quite a treat that we have as a speaker today our very own Professor Megan Connors. It's really great that she's closing the semester. So Dr. Connors did her PhD at Stony Brook University, which is very close to Brookhaven National Labs, where she's got most of her scientific involvement and still working in it, as you'll see. I want to see what's coming out. It's so bad. Then Megan was a postdoc and research scientist at Yale University before coming to Georgia State in 2015. And since coming in, she's been one of the superstars of our department, winning a career grant from the National Science Foundation, winning the Dean's Early Career Award, winning the College of Arts and Science Outstanding Junior Faculty Award. So she's got all those awards and more, and doing some really exciting research on jets. Are you going to talk about jets?
Yes.
Okay, so I'll leave it to Megan.
All right. Well, thank you so much, and thank you all for coming today, giving me the opportunity to share some of the exciting news coming out of sPHENIX. So sPHENIX was built to study the quark gluon plasma to remind everybody what quarks and gluons are. They're the building blocks of nature, right? So of course, inside of the atom, we have the nucleus, hence why we study nuclear physics, right? We're studying what's happening inside the nucleus, which is made up of protons and neutrons, which are made up of quarks and gluons inside here. And so we're really interested in how these quarks and gluons that are normally confined into these protons and neutrons, how they actually interact. So again, these quarks and gluons are really the most fundamental constituents of matter as we know it. And all of this experimental work furthers our understanding of the theory of the strong force, which is quantum chromodynamics. So I like to also show the little cartoon where literally it's the little building blocks, right? So these are the smallest pieces that you can have in this Lego set here. And so we can actually categorize all of these little Legos into how they look in terms of the sizes of these little particles and so on. And this is what we call, of course, the standard model of particle physics. Maybe it looks a little bit more familiar to you, more like this, right? Where again, we have all of these quarks that I just mentioned, and the strong force is mediated by the gluons. And analogous, of course, we have our electrons, which are mediated, the electromagnetic force, which is mediated by the photon. And so, of course, we have these quarks and gluons and our leptons and various bosons that mediate the different forces. So this is sort of fundamental. This is your particle physics class 101. Moving back to talking about the strong force itself, I mentioned that quarks and gluons, we can't see them. They're always confined inside of the protons and neutrons. And why is that? Well, I mentioned the electromagnetic force, which of course we're all very familiar with. As you take two magnets and you pull them apart, it gets easier and easier to pull them apart, right? The strong force, on the other hand, doesn't work that way, right? It works more like a spring between two particles or an elastic, right? The more you pull them apart, the more that string wants to pull them back together, right? So as we try to pull those quarks apart, what happens is that the potential between them gets greater and greater until it's actually more favorable to actually just pluck a new quark, anti-quark out of the vacuum, right? So therefore, we can't observe free quarks, right? So if I want to understand how a free quark behaves, I need to go about this a very different way, right? And the way we can do that is actually by turning back the clock. So moments after the Big Bang, our whole universe was in this state of matter called the quark gluon plasma. And what the quark gluon plasma is, it's basically the soup of quarks and gluons where they can behave as free particles in this hot, dense system. Very rapidly after that, the system began, the universe started expanding and cooling, and that's when these quarks and gluons became confined into protons. Of course, beyond that, they started forming nuclei and atoms and stars and so on until here we are today. So you can pick your favorite time machine, and try to go back in time, or we can actually use this QCD phase diagram as a map as to how we can go back and look at a quark gluon plasma. So here, the temperatures, we increase the temperature, that's taking us back to the early universe here, and we can replicate that with some collider experiments that I'll tell you more about in a moment. So, as I said, we need to turn up the temperature to get to this quark gluon plasma phase. So we have lattice QCD, which actually tells us where we should expect sort of this transition from hadronic degrees of freedom into quark degrees of freedom. And so that's we see that this critical temperature that we need to achieve is approximately 170 MeV, so mega electron volts, and so that's how sort of particle physicists usually refer to temperatures or energies, right? So if you want to translate that into something more familiar, right, we have it listed here in terms of Kelvin, but of course sometimes it's more familiar to relate it back to other things that you know. So this is actually 100,000 times hotter than the core of the sun. Which is roughly 15 billion times hotter than the cup of coffee that you might be holding at the moment. So that's how hot we need to get the system so that we can actually start having these quarks and gluons start behaving as if they're free particles. So I mentioned that we need these colliders to actually create this quark gluon plasma. So there's two such facilities in the world. One is the Relativistic Heavy Ion Collider, shown here, which is located at Brookhaven National Lab. As Sebastian mentioned, that's located on Long Island up in New York. And so there's two experiments that we're running back. So I'm going to take you a step back into to 2015. That's where my talk sort of begins. We had STAR and sPHENIX running, and now sPHENIX has been replaced by sPHENIX, which is what I'll tell you about towards the end of my talk. And then, of course, there's the Large Hadron Collider that's located right on the border of France and Switzerland at CERN. And again, it has multiple experiments located around it: ATLAS, ALICE, CMS, as well as LHCb. The difference here is that RHIC typically collides heavy ions up to 200 GeV, whereas at CERN, at the LHC, they can collide lead-on-lead ions up to 5 TeV. So this allows us to make quark gluon plasma at a much higher temperature. But RHIC was the first to really start studying the details of what this quark gluon plasma was like. So we have these two facilities. I said we collide particles. We collide gold ions typically at RHIC and lead ions at LHC. What happens when we collide them, right? Well, first, of course, we need to bring them up to relativistic speeds so that we can get up to the energies that are necessary to actually create this quark gluon plasma phase. So that's what's shown here. So they're sort of Lorentz contracted in this picture. So you have this initial state where you have some initial scatterings happening between the particles that are coming in. You have this quark gluon plasma phase, which again, just like the early universe, rapidly expands and cools and starts to hadronize so that those quarks and gluons start becoming confined into hadrons. And then these particles then, continue to stream out. And that's what's actually going to hit the detectors that I just mentioned that are located along the different points along the ring. And so they collide at different points along the rings, and that's where we've placed our detectors. And so, as I mentioned, at the LHC, we have ALICE, CMS, and ATLAS. At RHIC, we have STAR and sPHENIX. And if you look carefully at these little pictures, you often see little people there for scale to give you some ideas to how big these experiments are. And hopefully you'll also see, maybe you can't read them all, but like there's little labels here, right? And so when I talk about these detectors or experiments, they're really made up of multiple types of detectors, right, within in the systems that we use to help us measure the particles that come out. And so you can sort of categorize, even though these different detectors maybe have different subdetectors in them and different strengths, they all have some fundamental properties to them, right? So they have some sort of triggering detectors that tell you when a collision occurs. So like now it's time to start taking data. Those trigger detectors oftentimes are useful for also categorizing what type of events that you're seeing. I'll talk a little bit more about that later. We also have tracking detectors, and typically these all have a magnetic field associated with them. They have a large magnet which bends the particles, and so then the tracking detectors track where those charged particles go so we can measure their momentum. There's also oftentimes PID, particle identification detectors, to tell us which type of particle it is. And then we have our calorimeters, which the main goal of our calorimeters is to measure the energy of the particles that it sees. Okay, so just to make sure people are still paying attention, how many people cooked a turkey last week? Yes? And so how did you know that your turkey was done and ready to eat? Gut feeling?
No, it's the color.
The color? Did anybody use a thermometer? Yes? Good, okay. So hopefully some people use a thermometer, or at least that's what we do in our house. So, right, you check it with the thermometer, make sure you got it's at the temperature you want it, right? I told you to create a quark gluon plasma, I needed a certain temperature, right? So what do I need to do? I need to measure it, right? And so if I make a soup of quarks and gluons, right, I just can stick in my thermometer, right? Not quite. So how can I possibly measure the temperature of a quark gluon plasma that's made in these collisions that lasts femtoseconds, right? Like how could I possibly measure this, right? Well, another way that maybe during the pandemic people were taking your temperature with like infrared thermometers, right? What is that measuring? It's measuring the photons that you're giving off, right? And so the quark gluon plasma also gives off photons. So we can use photons as a way of measuring temperature. So that's precisely what we've done. And so I know these pictures are a little crowded, so let me walk you through this first one. On the left is actually from the sPHENIX experiment. The first thing that we often do is measure proton-proton collisions where we don't create a quark gluon plasma. And we make sure that we understand all of the QCD processes that are going to produce the photons coming from there, right? And so that's what's shown here, and these dotted lines are what you would expect as I scaled up if I just assumed that the gold-gold collisions are a bunch of proton-proton-like collisions, right? So if I scale up, what do I see? And so at these higher momentums for the photons, it's actually pretty consistent, right? There's nothing overly interesting happening here. But then at low PT, I see this actual enhancement of photons. So there's more photons being produced in these collisions. And we see that when the collisions are more overlapping, which are what we call more central events, there's even more of these thermal photons that we're seeing, right? And so this is what we're actually going to use the slope of this to extract the temperature. And so we were able to do this at RHIC as well as at the LHC. And so here's a plot from Alice that shows the extraction of the inverse temperature. And so here they found that the temperature got up to, or the temperature that they're probing with this measurement gives us 300 MeV, right? And at RHIC we saw something slightly smaller, but above the 170 MeV that we expect is needed to create a QGP, right? So, okay, so we've created something that's hot enough. Yes?
Can you remind us what low momentum versus high momentum, how we're supposed to picture that in these experiments? Is it directional?
So, or you can think of it as like energy of the particle, of the photon in this case, right? So, so we typically measure PT, which is like the transverse momentum, because that should be in total conserved, right? With if you just have the collisions mostly coming in like this, right? So we measure the transverse momentum, and so it's just ones that have less energy versus more energy, right? So higher energy photons, they just come out. They don't interact with the quark gluon plasma because they don't actually interact via the strong force. So they come out, fine. And then we see this enhancement at low momentum, which is associated with the thermal processes of the medium. You might also want to ask other questions about the medium, right? So, okay, if I've convinced you maybe that we've created a quark gluon plasma, I want to know how the particles interact inside the quark gluon plasma. And so I expect that if I sent a quark through the QGP, it might actually lose energy as it's going through this color field, right? So we have radiative energy loss as well as collisional energy loss, right? And so one way that we actually characterize this energy loss is with this Q hat, this transport coefficient Q hat, which I'll just keep that in mind, that I'll mention it again later. So what happens? So what happens is, I mentioned when they first collide, there's some sort of initial collisions that happen, and you can have these hard scatterings. So I say hard, basically I mean high momentum, or right, energetic collisions, where you have like this hard scattering, so they really scatter off of each other and produce very energetic particles coming out. So if you say you have a quark here and a quark here that collide, then they can produce two outgoing quarks, right, that will then, hadronize, fragment into other particles. And this sort of collective spray that's associated with this initial hard scattered particle, this spray is what's called a jet, okay? So this is what a jet is. It's a spray of particles that came from this hard scattering event. Now that happens in proton-proton collisions, and it also happens in this initial stage of the heavy ion collisions. And so that means that this outgoing parton can act as a probe of the medium, right? I can then study how this interacts with the medium. How would I do that? Well, like I said, I have these proton-proton collisions that I can compare to, and I can say if I measure jets and proton-proton collisions and can then compare them to gold-gold collisions, how do things look? Do they look the same? Are they modified in some way? What's happening, right? And what we find is that they actually do, in fact, lose energy, and so this is often referred to in our field as jet quenching. Okay, how do you find these clusters or sprays of particles? So this is actually a picture of an event from STAR. So this is like a proton-proton collision. And so you can all probably by eye say, okay, there's probably a jet here and a jet here. And then maybe some of you would include these particles. You'd have a wide jet cone. Some of you might say, no, I'm just going to use these ones and say that these are just other particles that happen to be in the event. But I think we can all agree there's two jets here. Yes? Okay. How about this picture? Right, so this is a heavy ion collision at RHIC at STAR. And so embedded in here somewhere are jets, right? And so these are all the tracks that are coming out that they see in their tracking detectors. And so this is a big challenge, right? Is we need to remove a large underlying event that's coming from the QGP, right? From the jets to find out what's happening. How are the jets themselves modified, right? And we actually measure, oh, that's interesting. We actually measure these sort of effects in two ways. We can measure like just the spectra of jets or particles in proton-proton collisions and compare them to what we see in gold-gold. And I told you we have this effect of jet quenching. And so you can think of that as either sort of an absorption of the particles, but of course they don't just like get absorbed. Something needs to happen, right? It's really they're losing energy, so it's kind of an energy shift to the right. But in either case, you'll get an RAA. If you take the ratio of these two, you'll get an RAA that's less than 1, and that's what indicates suppression. You can also look at the angular distribution of the particles, right? And so, like I said, in that first picture, you saw that there was a jet on one side and a jet on the opposite side, and you can measure sort of the angular correlations and see if you see both the near side peak and the away side peak, right? And so, yeah.
What does AA refer to?
AA just means like a nucleus, right? And so AA means that I have two nuclei coming in. So at RHIC, it would be gold. In LHC, it's usually lead. Good. And so the RAA, I'm taking the ratio of the AA collisions to the proton-proton collisions. As I told you earlier, for direct photons, we don't really see any effect. We get an RAA of 1. However, for the hadrons that contain quarks, we see the strong suppression. So these are sort of the early results indicating these jet quenching effects at RHIC. And then if I look at the STAR result here for the two particle correlations, as I said, you see this near side peak, which is associated with some trigger particle that you've selected, and now you're measuring all the other particles, and some of them are from the nearby jet. And then 180 degrees away, you expect to see this away side peak. And that's exactly what you see in proton-proton collisions, but in gold-gold collisions, it's strongly suppressed, right? And so again, this is the evidence that there's some jet quenching effects happening in these heavy ion collisions. But we want to study more, right? So like I said, those are early results. Those are sort of your signature results. We want to understand a lot more about how the particles lose energy. And one thing you might want to ask is, how does the temperature of the quark gluon plasma affect that energy loss mechanism, right? And so RHIC, of course, is at a lower energy than the LHC. And so we need to, if you have a good model, right, it needs to be able to explain the measurements that we see at both RHIC and the LHC. And so there's a whole theory community, right, that, of course, Yang Ting is a member of, trying to explore, make sure that their models match both RHIC and LHC measurements. And why might they be different at different temperatures? What could be happening? Well, the sort of interaction between the plasma and the quarks themselves is different at RHIC, which is shown here in red, compared to the LHC, which is shown here in black, right? So in some ways, the quarks or the protons that are produced sort of can experience more of the effects of the QGP at RHIC energies. And so you see that this is sort of, that's what this bold part shows, is sort of how much of it is being influenced by the QGP phase. Because as I said, the whole system rapidly expands and cools, right? So like I said, my story starts sort of back in 2015, talking about the long-range plan for nuclear science. So for all of nuclear science in the US, what are the most important things to do? And in 2015, the community agreed with that the number one recommendation is to build on capitalize on investments made. One of those investments, of course, was RHIC. And to do that, there were two main missions that RHIC needs to complete before it completes its sort of scientific mission. One is to probe those inner workings of the QGP by looking at it at shorter and shorter length scales. And the end of the sentence tells you that to do this, we need to build a state-of-the-art jet detector at RHIC called sPHENIX. The second part of this statement is about mapping out that phase diagram that I mentioned earlier. And if you recall, Helen Keynes gave a talk to us about a year ago related to measurements that STAR did on measuring that phase diagram. So what is sPHENIX, this state-of-the-art jet detector, need to do? It needs to provide high statistics, extend the kinematic reach that RHIC currently has, so that we have sufficient overlap with jets at LHC energies so that we can make these really nice comparisons across the two different systems or temperatures, right? So here's what we set out to build. And so this is sPHENIX. So we have shown here the different detector components, as I mentioned. So we have the outer HCal, there's the inner HCal, so these are our calorimeters, and the EMCal that are going to measure the energy of the particles that come out. We have our tracking detectors called the INTT, the TPC, and the MVTX that you're going to see those charged particles go through. And what's not shown here are actually our event plane or event characterization detectors. I was like, I thought I updated the slide. I did. I just didn't delete the other one. So this is a prettier version showing you those. So here's the event characterization detectors that I mentioned. So there's the min bias detector, MBD, which will come up later. And this is the event plane detector. So it tells you how that overlap region is oriented. So this is all the different subsystems, right? I'm going to focus a little bit at the beginning here on the calorimeters. So as I said, this is what measures our energy. In particular, what I'm interested in measuring, of course, is the energy of those jet particles that come out. So we need to measure the electromagnetic energy that comes out, so our photons and electrons, that gets measured in the EMCal. And then the hadronic calorimetry system, that's what's going to measure our hadrons, basically all these other particles that are part of these jets, right? So this is really important. And the way we do that is putting basically a bunch of material in the way, and in between this material, these heavy plates, we have scintillator tiles, which are going to see the light that gets deposited here. And so those tiles that are sandwiched between these steel plates, there's a picture shown here. I'm sure many of you have seen such pictures before, or at least seen them boxed up in the hallways, which again, I'll show you more pictures of in a moment. So this is for our HCal, and this is what an EM-Cal block looks like. This is actually tungsten, so these little things are actually quite heavy. And then they have the light guides, which go to the SIPMs. These SIPMs are also what's used on the scintillator tiles. They measure the light that comes out from these fibers that collect the light that's produced in the scintillating tiles. So that's the basic design. So how did we eventually get from sort of design to detector system, right? We did a bunch of prototype testing. So this was back in, again, like 2016 or so. You may remember Anthony Hodges. So we're at Fermilab with a test beam. So we put in particles of known energy and then measured what we got out and confirmed that what we see in the simulation and in the actual data when we have known particles matches. So great. We know what we're doing. So let's go ahead and build it. And so that's what we did. So from 2017 through 2021, we had a whole army of students measuring these scintillator tiles. And so actually, this is an early version of the test stand. Here's the test stand here. What we're doing here is measuring these scintillator tiles. We have them stacked up, and we're actually using cosmic rays to actually test the performance of the tiles. We spent many group meetings discussing any sort of features that we saw and behaviors, and testing all the different shaped tiles that we have. We also had devices to make sure that they actually will physically fit between those steel plates that I mentioned earlier. Of course, during this time, the pandemic hit. We were one of the first groups back on campus to continue this project, which was time sensitive. We had to keep the whole sPHENIX project on schedule. During that time, since people weren't in class, we actually put a bunch of these boxes in the instruction labs. As I know Brian will very much remember, that we were moving them around, shuffling them around the different labs. And so this was a huge project that, and quite impressively, the GSU team and particularly our students kept this project on schedule. And the reason why it's so important is because the HCal, it was the first detector to be installed, right, for sPHENIX. So it was really important that we got this done on time. So sort of pre-pandemic, we actually assembled the first HCal sector. So here's a picture of me putting in one of the tiles into these steel plates. And so this is the first sector, and here you see sort of the readout boards and everything fully set up. And then this is how it's actually starting to be assembled. So there's 32 of these sectors that then get put together, right? And so this is a very heavy project, obviously. And then sitting now on top, what you see here is actually the solenoid magnet. This was originally used previously in the Babar experiment at SLAC. It made its way across the country and is now being used by sPHENIX. And then they continued to put together the hadronic calorimeter around the top there. So this is like I said, there's an outer HCal, you have the magnet, and then the next thing to be installed was the inner HCal. And in summer of 2022, we had two of our undergrads actually up at Brookhaven Lab working on sorting out all the cables that then had to be connected to the HCals after they were installed. And so this is actually the inner HCal being slid into the magnet. And then that actually acts as a support system for the electromagnetic calorimeter. And so that's what you see being installed here is the first sector of the electromagnetic calorimeter inside the inner HCal. So that's where we were in summer 2022. So this is Damien and Jorge from GSU. Then that November, the EM-Cal installation was complete. In January of 2023, the TPC was then installed. The TPC is this time projection chamber, so it's a big gas detector. So that's what's installed here. What you'll also see now is the beam pipe has been installed. So now this has been rolled into position where it needs to be. And we have sort of this beam in position. Then around that was also inside there was what we call the INTT. So this is a silicon-based detector. So that was installed in March. And I was at a conference right at the end of March giving a talk telling people what was going on and literally giving them sort of minute-by-minute updates on the MVTX installation. So this was what it looked like at the end of March as it was being installed. So you see sort of the two pieces of the MVTX that came together. And so this is all very, very delicate equipment that was very stressful to, we were all very relieved once everything was in place, right? And so this was, like I said, at the very end of March of this year. And so here it is all together, all the pieces in place. And so we were ready for first collisions. We saw first collisions on May 18th. So that was really, really exciting to have this all come together and actually start taking data this year. And so our team of students and our postdoc, Virginia Bailey, who's been stationed at BNL this whole time and has been very helpful in making sure that GSU is connected to what's going on and ensuring that the HCal is being properly commissioned and everything at the BNL. So she's pictured here along with, I think there were multiple sort of groups of us that went up over the summer. So this is just one sort of cohort, let's say. Not pictured here are Murad, Ghassoon, and Munir, for example. Who are pictured here are Kristen and Devon, who are undergrads from GSU. So this is actually a picture of Devon giving a presentation looking at the LED data, seeing which regions of the HCal were working properly and which maybe we need to switch the cables on because they got plugged in the wrong way. Okay. But that's okay. We got them all fixed. So it was really exciting. So both of them, myself and actually Shumail also, we actually climbed up into the detector at some point and were helping with these sort of repairs. So that was really fun. So we all took shifts helping take data over the summer. And like I said, also helped trying to understand what's happening with the HCal. It was very successful. I guess you can still see that it's correlated, even though it's been rotated here. So this is actually data from the experiment, right? So what you see here is actually in blue the outer HCal energy, and in red the inner HCal energy that's been deposited. And in this plot here, you see the inner HCal energy and the outer HCal energy. And you see the beautiful correlation, right? Which is exactly what you want to see. You expect that if there's energy being deposited in one of them, that those particles are still going and go into the next detector, right? So this correlation is really beautiful to see, and so that was something that Virginia made as sort of an early measurement that we were starting to show to the community and everything to show things are working properly. So this is really exciting that the HCals are working. You want to push this a little bit more, right? To just say, okay, look, they've got this correlation. But what's also nice is to make sure they're correlated with other detectors. And so I mentioned earlier one of those event characterization detectors or trigger detectors was our min bias detector. And so when you see more energy in the min bias detector, we see more energy in our HCals, right? Which is what you would expect. So that's great. Ideally, what all of this is shown is sort of in these arbitrary units, right? Because things aren't fully calibrated yet. What we're really measuring are like ADC counts, right? But ultimately, we want to translate that to actual energies. So one way to do that is actually doing cosmic ray tests as the whole detector. And so we have some really nice data actually from our cosmic ray studies that we set up and sort of an initial calibration based off of those studies, which is shown here. So the commissioning of the HCal went beautifully. There's still some commissioning work that needs to be done as RHIC sort of ended its run early in August. But we did fish through the data to see if we got anything that looked like a jet. So of course, long term we'll have high statistics data, but at the moment, right, we have what we have. And so we did find something that looks like a jet to sort of see what it might look like. So this is looking at all three of the calorimeter layers together, the EM-cal plus the two HCals. And you see sort of this dye-jet type structure that you would expect to see. As I mentioned, sort of looking at these dye-jets tells us something about the energy loss, right? So you can compare the energy on one side to the energy on the opposite side, and this is what we call this dye-jet imbalance. This is just a picture of an atlas measurement to show you sort of what we're aiming for to do, and what you see is that in these black points, which are the most overlapping lead-lead collisions, you see this significant difference compared to the proton-proton collisions, right? And so that, again, tells us that there's some imbalance between the two jets, meaning that there's some energy loss happening, right, as they traverse the medium. As I said, we've started looking at the HCALs. We see some things that look like jets, but ultimately there's a lot of work that goes into actually getting that plot that I showed you from Atlas, right? Going from what we see on that previous slide, right? Going from here to here is a lot of work. And so some of the things that our group is involved in is studying the underlying event that needs to be subtracted, right? And so this is a plot that Schumail made, looking again for those most overlapping events. You see the highest amount of energy compared to the less overlapped events. So this is work that's been done in simulation, and we've started applying it to data. Also done in simulation is Damien's looked at what we call the jet energy scale. So you can, in simulation, of course, you put in sort of truth particles, and then you see what you're able to reconstruct from your detector. And by comparing those two values, that tells you about your jet energy scale. So you don't expect to reconstruct everything perfectly, but hopefully it's somewhat close to one. So we're about at 80% for the highest momentum jets, which are typically easier to measure, right? The low momentum stuff gets harder, especially in these events where you have this large underlying event that needs to be subtracted. And so that's what you see happening here on the left. You start to see these effects of the underlying event, in particular for these most central, these most overlapping types of events. And so again, this is simulation work that was done by Damien. And so they're working together with our collaborators on sort of a first sort of jet performance study based off of a combination of some simulation and early data as to how we think we'll be able to do moving forward with our jet measurements with sPHENIX. So this is really exciting to give you a little flavor of what is yet to come, right? So I mentioned the point of building sPHENIX was to extend the kinematic reach. So, for example, direct photons that were previously measured by Phoenix really only went out to about 20 GeV. So you see, we basically doubled how far out we can reach. And so what's also plotted here is the jet energy range. And so this has nice overlap also with the LHC kinematics. I mentioned that you can use different jet finding algorithms, or I said, okay, maybe your cone size is different sizes. And so you could ask questions about what do different sort of size jets, how does the suppression look, right? Does it look different? And so these were measurements that were done at the LHC. You see in green here these Atlas measurements, and in purple these Alice measurements. And so when they push down to these lower momentums, they do see something interesting when they compare sort of the small cone jets to the big cone jets. And you see that they see something different, right? So in one case that you see that the big cones are more suppressed. In the other case, you see that the smaller cones are more suppressed. And so this is a place where sPHENIX can actually weigh in, right? In this low momentum region, that's what we're equipped to do, and kind of see where do we lie in this effect. So this is looking at the jets as a whole, right? We can talk about their overall suppression, this RAA, or looking at them as a whole in terms of these different cone sizes, but we can also look inside of them and see what else is happening. We can also look at different types of jets where, for example, we have a trigger particle on one side and then look at jets on the away side. So if I have an event that produces a direct photon on one side and a jet on the other side, the direct photon I mentioned doesn't interact with the quark gluon plasma, right? So the energy it has is the energy it had to begin with, right? But the jet energy, it lost some energy, right? And so this is actually a way that we can directly probe how much energy was lost, right? And so that's what this ratio is comparing the jet momentum to the photon momentum. So it seems like the effect that you might expect to see at the LHC would be smaller than at RHIC energies. And so this would be a really nice place to really push the models in terms of how well that they can do in terms of reproducing this picture, but also then using this as a probe and looking at more differentially as well. And so this is a projection an actual projection of what we expect to be able to do with the sPHENIX data sets once we've collected all of the gold, and proton data. We can also do, like I mentioned earlier, we have an event plane detector, so that tells you how sort of this almond shape is oriented. Why is this interesting? Well, if you have jets being produced and they're going out at different angles here, you'll see that this jet, for example, had to traverse a lot more QGP than this jet, which would mean that you would expect this one to experience greater energy loss, right? And so we can study sort of the path length dependence to the energy loss by doing a measurement which we call V2. That's what's shown here. These ATLAS results are actually something that Virginia was involved in as a graduate student. And so the LHC measurements are shown here. Again, as I said, in this lower momentum region, it's a lot harder to do well here. And so this is, again, a place that sPHENIX can really contribute to understanding what might be happening and what the path length dependence looks like in these at the energies that we collide at RHIC. You can also look inside of the jet cone and see what's happening, right? So there's sort of these full jet measurements I mentioned. You can also do these sort of substructure measurements or look at individual constituents, looking at something like a fragmentation function. These intermediate constituent substructure type measurements, there's a picture of it shown here, right? So you sort of reconstruct mini jets inside of your jet and just, compare the properties. So this ZG variable, for example, is looking at sort of the min PT over the sum of the PTs. And so again, you see this is what we would expect to be able to measure in sPHENIX for the black points or for proton. In red are the gold points. And so we have some really nice data that we expect to be able to get in the future runs. So the next run will be this proton baseline data, and then the year after that we'll take more gold data. I've only told you actually a small piece of the overall sPHENIX program, because that's what filled up our colloquium time. And so this is what I'm most involved in is studying like these jet structure type measurements. But also our group here at GSU, Xiaoshun and Gusun, are very interested in looking at what we call quarkonia measurements. So sort of you can look at the different quarkonia states and sort of this binding energy difference and where they quote melt in the QGP and what the suppression is. So they want to look at that. Also, we can use different sized probes. So most of the time when we do these jet measurements, you're actually looking at jets produced by the lower mass quarks. But there are high mass quarks or heavy quarks that we can look at. So there's a whole program. That MVTX I mentioned is specifically designed to help us detect when there's a bottom jet quark in the events, and so we can do B-jet tagging. So that's something Murad and his students are also interested in. And these sort of three pillars, let's say, are all related to studying what's happening in the Quark Gluon plasma. But of course, the proton data that we take is also interesting on its own. And we also hope to be able to do measurements in what we call small systems like proton-gold collisions and study what we call cold QCD effects, where you don't actually have this Quark Gluon plasma. So that brings me to my conclusion. So hopefully I convinced you that we have fully installed sPHENIX and that we had a successful commissioning data run in 2023. Specifically, the HCal is working really well, and we are ready to start taking data for the next run, which will hopefully start in March of 24. We've played, GSU as a group played a crucial role in developing and commissioning that HCal, and our students are ready to do some thesis analyses utilizing the upcoming data sets. Like I said, we're starting to see some jets. We have work going in this vein. It's really exciting time, and once it all comes together, I hope you see that we'll have some really interesting insights, I think, to how the energy loss mechanism in the QGP works. And also, I just wanted to plug that the HCAL is one part of sPHENIX that's actually going to be around for a long time, because the plan right now is the first detector to be installed at the future electron ion collider called EPIC is actually going to reuse the HCAL. And so the plan is to actually take all the scintillator tiles and retest them and then reinstall them and put new SIPMs on them. And there's also forward calorimetry that they want to install in the EIC. So you may see more tiles at GSU, hopefully sometime in the not too distant future. And so I want to thank everybody for joining us, and for the students in the audience. If what you thought, what I said sounded interesting to you, we're always looking for new students to join our work. And again, what I talked about today was just a small piece of what our group as a whole does, looking at cosmic rays, for example, building detectors. Also, Murad has studies on the weak force, and also long-term we'll be working on EIC detector R&D. So thank you.